Hello everyone. In the last class you were introduced to glycols and we discussed that what are the different methods of preparation of glycols and what are the different kinds of reactions they undergo, in which we saw that the reactions of glycols are similar to those of the monohydric alcohols. Continuing with that series, today's class we are going to do some more reactions of glycols which are typical of glycols, and then we are going to continue on from there to phenols. So, let us start from where we stopped in the last class, talking about the reactions of glycols. And in this category today we are going to learn about the oxidation reaction of glycols. So, if you recollect, we did the oxidation of alcohols, the monohydric, and today we are going to learn about that of glycols. Okay, so first case I am going to discuss is with acidified KMNO4. So, acidified KMNO4 is one reagent which is used to oxidize glycols, and the product which we get through the oxidation of glycols with acidified KMNO4 is either an acid and or could be a ketone. So, if you start with a 1 degree and a 2 degree alcohol combination in a glycol, you end up with an acid, and if you start with a 3 degree OH, you get a ketone. So, in the acidified KMNO4 oxidation of glycols, this is what happens. You treat the glycol with KMNO4 acidified and you end up with 2 moles of formic acid with the fission taking place between this carbon-carbon bond. So, there is this fission or cleavage of the carbon-carbon bond between the 2 carbons containing the hydroxyl groups take place. Okay. So, carbon-carbon bond cleavage takes place. This is what happens. So, this is a case when both of them are primary in nature. If you start with a one which is a secondary alcohol and a primary alcohol, so in this case you will get the corresponding carboxylic acid depending upon the R group, and you get 1 mole of formic acid. So, again the fission or the cleavage takes place between the carbon-carbon bond here. If you start with a tertiary alcohol and a secondary alcohol, you end up with a ketone and the acid. So, as we say that with 3 degree alcohols we get the ketones, and with the 1 degree and 2 degree we get the acid. So, this is the oxidation of the glycols with KMNO4 acidified. Another reagent which is used for their oxidation is periodic acid. So, what happens when they are treated with periodic acid, which is represented by HiO4, or instead of periodic acid we can also use sodium periodate. So, instead of this you can also use sodium periodate. Both the cases the oxidation proceeds in the same manner. So, with periodic oxidation, if you start with the glycol and you treat it with HiO4 or NaIO4, as was happening with KMNO4, the cleavage of the bond occurs at this position, but instead of the acid as you were getting previously, you end up with the mixture of the aldehyde. So, in this case, since it is symmetrical, you get 2 moles of formaldehyde along with formation of water, and the periodic acid is reduced to iodic acid, or if you start with sodium periodate, it also gives you the reduced form NaIO3. So, essentially with periodic acid what we are getting is that your +7 oxidation state is changing to +5 oxidation state of iodine when it forms the iodic acid, and the products which are obtained are, as you can see from this, you get aldehydes and or ketones. So, here again if you start with a 1 degree and a 2 degree alcohol, you get an aldehyde, and if you start with the 3 degree alcohol, you get the ketone. So, this is what a per iodic oxidation of glycol is. We take few more examples. We see a combination of a 2 degree and a 1 degree, treat it with per iodic acid, and you can guess that as a result of the cleavage here, the product is going to be this aldehyde along with the formaldehyde and water and 1 mole of HiO3. So, you can see that 1 mole of HiO4 is used when you have one glycolic unit, okay, when the fission is taking place between one carbon-carbon bond pair. If you start with a tertiary and a primary alcohol combination, treat it with HiO4, and as we said, if you have a 3 degree alcohol, then you would expect it, once it cleaves, it is going to furnish a ketone along with formaldehyde, the rest of the byproducts being the same. If you start with both 3 degree alcohols, what you were introduced last time, when you have a diol with both the carbons as tertiary, this is called a pinacol, and when you treat a pinacol with HiO4, you get 2 molecules of the ketone along with HiO3 and water. So, the importance of this reaction lies in the carbohydrate chemistry. Okay, so, this reaction is very important. It is used in carbohydrate chemistry for elucidating the structure of the sugars. So, carbohydrates contain many hydroxyl group, it is a polyhydroxyl containing compound. So, to find out what is the number of the hydroxyl groups present and what is the kind of the positioning they have with them with each other, we use this per iodic acid oxidation. Okay. So, let us see some typical examples of per iodate oxidation. Okay, so we will do this together. This is your starting substrate. Okay. You subject it to HiO4 oxidation. What do we expect? There is one fission possible here, another possible here. So, this would require 2 moles of HiO4, and the terminal carbons bearing the hydroxyl get oxidized to aldehyde, and the middle one, it gets oxidized fully to the acid. So, this is what happens with the per iodate oxidation, that if you have all the carbons in the middle which bear the hydroxyl functionality get oxidized all the way till acid, and that is why it is used in the structural elucidation of sugars. So, if you have further elongated chain, you have a 4 carbon system. So, you would expect 3 of these carbon-carbon linkages to cleave, for which you will require 3 moles of HiO4, and the product would be from the terminal you would get the formaldehyde. There are 2 internal middle carbons containing the OH functionality. So, you get 2 moles of formic acid here and 1 mole of formaldehyde from the other terminal carbon atom. So, this is what happens in case of sugars. If you have a terminal formyl group, this molecule. Okay. So, again we are looking at 2 carbon bond cleavage, treat it with 2 moles of HiO4. Now, the terminal formyl group is going to oxidize to formic acid, and the internal one is also going to oxidize to formic acid, and this terminal CH2OH yields formaldehyde. So, if any aldehyde or ketone is present adjacent to the OH, carbon bearing OH, it also gets oxidized. Look at this example. If you have this ketone following the same rationale, treat it with 2 moles of HiO4 and you get formaldehyde, another formaldehyde, and the internal ketone carbonyl is oxidized to CO2. So, this is what happens if you have a ketone or an aldehyde, it gives you a CO2 or a formic acid. If any carboxylic group, an ester group or a methoxy group for that matter is present next to the carbon bearing the hydroxyl functionality. So, if you have to carry out the periodic oxidation of this reaction does not happen. So, these compounds are not oxidized by HiO4. Likewise, if you have a methylene functionality which is coming in between the 2 hydroxy carbons, this again is immune to periodic acid oxidation and you do not see a product in this case as well. Another important thing which has to be noted here is that for periodic oxidation, it is the cis glycols, we are taking into consideration the stereochemistry as well. With cis glycols, these are oxidized by HiO4, but if you start with trans glycols, these are not oxidized by HiO4. So, which means that if you start with this cis 1,2 diol, okay, we are talking about cis 1,2 diol in a cyclic system or in a acyclic system. So, these can be cleaved, okay, to give you with periodic acid to give you the corresponding oxidized product. But if you, so these are okay, but if you start with the trans isomer, for whatever reason, if this stereochemistry is fixed here, if you start with the trans isomer, then these are not oxidized. So, the question is why? Why does that happen, that it is only giving you the oxidation with the cis stereochemistry? So, if you just look at the way this oxidation takes place, you start with a cis glycol. Okay, let me just redraw this. If you start with a cis glycol, okay, and you treat it with periodic acid, so the first step is that there is this attack of this lone pair of electrons on iodine and you get an intermediate and then there is a subsequent attack by the other hydroxyl oxygen lone pairs and you further get this cyclic intermediate, which is followed by loss of this water molecule to generate this cyclic ester. Okay, so you get this per-iodate ester as the intermediate, and it is then the decomposition of this per-iodate ester. Okay. It is this decomposition of the per-iodate ester which is considered actually to be the rate determining step in case of simple glycols, and it is this per-iodate oxidation which gives you finally your 2 carbonyls along with the formation of HiO3. So, this is considered to be the rate determining step when we are dealing with simple glycols. However, if you are dealing with pinacols, okay, so in case of pinacols where you have 2 tertiary carbons, tertiary diol, in this case it is because of the steric hindrance offered by these alkyl groups that the rate determining step in fact is the formation of the cyclic intermediate. Okay, it is the formation of cyclic intermediate which is the rate determining step when you are starting with pinacols and subjecting them to HiO4 oxidation. So, you start with the pinacol, treat it with HiO4, there is formation of this cyclic intermediate, and this is actually the rate determining slow step, and then the decomposition of this to the corresponding aldehyde ketone is the faster step. Another variance in this oxidation, the third one is if you do this with lead tetraacetate. So, we discussed with acidified KMnO4, then with periodic acid, and then with lead tetraacetate. Oxidation with lead tetraacetate is actually complementary to periodic acid oxidation. So, what do we mean by that? So, you take lead tetraacetate in acetic acid. Oxidation of glycols with lead tetraacetate becomes important for the glycols which have low solubility in water. Okay, so, glycols which have low solubility in aqueous medium will be more favorable to be oxidized via a lead tetraacetate oxidation. So, this is complementary to periodic acid oxidation. Why? Because in periodic oxidation it was an aqueous medium which was being used for the reaction, but in case of lead tetraacetate oxidation of diols, the reaction is carried out in organic solvent like benzene, toluene, dichloromethane, tetrahydrofuran, etc. And in this case it is both the syn and the anti-glycols, that means both the cis as well as the trans 1,2 diols can oxidize. The reaction with cis however is much faster. Cis are more reactive as compared to trans, but both reactions do take place, as in this case we get both the open chain as well as cyclic intermediates being formed, okay, which allows both the cis and trans forms to react. So, let us look at one of the examples of lead tetraacetate oxidation of the glycols and the products it yields. You treat this glycol with lead tetraacetate, glacial acetic acid, as was happening with periodic acid. You get this carbon-carbon cleavage giving you 2 molecules of formaldehyde, and lead tetraacetate is reduced to the diacetate along with formation of 2 molecules of acetic acid which are released. If you start with this diol and same thing lead tetraacetate, you get this product mixture which is a ketone and an aldehyde. So, a 3 degree is again giving a ketone, 1 degree is giving you an aldehyde as was happening with HiO4, and if you start with a Pinacol, as we saw earlier also with HiO4, you get the same products, which is the ketone in this case. Think about the mechanism here again. What is it that is happening during the reaction mechanistically that is giving you this product? So, you are starting with the diol, you are treating it with lead tetraacetate. The first step, as you would anticipate, is the attack of this hydroxyl onto lead and the replacement of one of the acetates by the glycolic OH. So, it leads to the formation of this intermediate, right, and this does not stop here. There is loss of another molecule of acetic acid, as we saw in the final equation, 2 molecules of acetic acid are being lost. So, another molecule of acetic acid is lost and we get now the cyclic intermediate which undergoes decomposition, as was happening previously also with the iodate ester, and you end up with the mixture of your carbonyl compounds and generation of lead diacetate. This mechanism explains why cis diols would react fast and give you these oxidation products. What happens in case of trans diols, that once you generate this intermediate in the first step, okay, you generate this intermediate. Now, in case of trans diols, there is a possibility that the acetate loses in this manner and still you are able to get the complementary product with this carbon-carbon bond fission, which was not possible in case of HiO4, and still you end up with the same product mixture. However, the yield or the rate of the reaction for trans is less than that of cis. Cis are more reactive, cis 1,2 diols are more reactive than the trans 1,2 diols because of the formation of this cyclic intermediate, which makes the reaction more facile. So, this is about the oxidation reaction of glycols with the different reagents, acidified KMnO4, HiO4 and lead tetraacetate. Another reaction of the glycols which is very important and popular, and I referred to in the last class also, is the Pinacol-pinacolone rearrangement. So, you already are familiar with the word Pinacol now, that it is a diol in which the 2 hydroxyls are on the 2 tertiary carbons, but how is it synthesized? Okay, so, there is a very special way of making these pinacols starting from ketones. So, you start with the ketone and treat it with a metal like a magnesium or aluminum, a metal which is less reactive than sodium, or you can use even the amalgam. And in this first step, there is a single electron transfer from the metal to the carbonyl. Okay, so, from the metal to the carbonyl, there is a single electron transfer which results in the formation of this radical anion. So, you get an anion radical which again reacts with another molecule of ketone to give you another anion radical, and then these 2 anion radicals, they dimerize. They 2 dimerize in the absence of any proton donor, and when they dimerize they give you this molecule, which is magnesium pinacolate, which then undergoes acidification to yield the desired pinacol. So, this is a method through which the pinacols are prepared starting from ketones, and then what we are learning now is how do these pinacols undergo rearrangement to give what we call as ketones, which are pinacolones. So, Pinacol-pinacolone rearrangement is essentially the rearrangement of a pinacol, which we now know is a 1,2 diol, a tertiary 1,2 tertiary diol. So, a pinacol is converted to a ketone, and what is the reagent? The reagent is concentrated H2SO4 or anhydrous zinc chloride. So, the reaction takes place in concentrated H2SO4 and anhydrous zinc chloride to convert a pinacol to a pinacolone, and this is what it looks like. So, you start with this pinacol and you treat it with concentrated H2SO4. It undergoes elimination of a water molecule, and in the process what you get is this ketone, in which there is a migration of an alkyl group from carbon 1 to carbon 2. So, the reaction, this is called a rearrangement. So, whenever we talk about rearrangement, it implies that it involves a migration of something. So, there is a migration of alkyl group to convert a pinacol to this ketone, which is called a pinacolone. Now, in this case your R could be anything, it could be a methyl. So, it could be a tetramethyl, it could be a tetraphenyl. So, if you have this, then it is your symmetrical pinacol. You can also have different R's. So, your R could be H, methyl, phenyl, or a mixture of these. So, the migratory aptitude. So, the question is which R is going to migrate. So, the migratory aptitude for between these different functional groups follows the order hydrogen, followed by the aryl, followed by alkyl, and in the alkyl again the more electron donating the alkyl, the better is the migratory aptitude of that. So, this is very interesting reaction of diols in which there is a rearrangement to give a ketone. Let us briefly analyze what is happening through this reaction. So, what is the mechanism of this reaction which is carried out in the presence of concentrated H2SO4. So, you are starting with your diol, di-tertiary diol, and you are treating it with the acid. Okay. You are subjecting it to acidic conditions. Okay. So, the first step one would expect is the protonation of the pinacol. So, this is the first thing that one would anticipate is happening, that your hydroxyl gets protonated. So, there is this protonation of the pinacol, and this is a reversible reaction. Okay. So, this is plus, this is minus, this is a reversible reaction. So, the first step being the protonation of pinacol, reversible step. The next is the loss of water molecule, okay, to give you a carbocation. So, there is a loss of water molecule and it results in formation of carbocation. This is the second step which also involves the migration of the alkyl group simultaneously. So, but I will show them one by one what is happening. So, this step is the loss of water and formation or generation of this carbocation, and this is followed or is happening complementarily, that this alkyl group here is migrating towards this carbon which is bearing a positive charge, so that you get this kind of a cyclic intermediate. So, this step is the rearrangement or the migration of the alkyl group. But the question is, why would the alkyl group migrate? So, you are going from a tertiary to a tertiary carbon, okay, it is already a tertiary carbonium ion, but still there is a migration from a 3 degree to a 3 degree taking place. So, why is it at all happening? So, this is where comes your concept of neighboring group participation, that the alkyl group migration on this carbon is actually what facilitates the elimination of this water molecule. Okay. So, this is the concept of neighboring group, that this, when it migrates on this carbon, it pushes this H2O out, and this facilitation is what is responsible for the migration. Otherwise, there should be no reason why a tertiary carbonium ion is changing to another tertiary carbonium ion if there was no such kind of a stabilization being provided. So, once you get this intermediate through the migration of the alkyl group, so the other tertiary carbon is what bears the positive charge now. So, there is basically shift of the positive charge from one tertiary carbon to another because of migration of the alkyl group, which is actually a neighboring group assisting the elimination of the leaving group here, and this then undergoes loss of a proton okay. So, if we just show it like this undergoes a loss of proton to give the Pinacol-pinacolone, okay, and this resonating structure stabilizes and drives the alkyl migration. Okay. So, the important thing about this reaction, if you notice that the first step was reversible, it involves an intermediate formation of a carbonium ion and the migration of the R group. So, the R group should be located trans to the leaving group. So, the migrating R group should be trans to the leaving hydroxyl group, and both the migration of R and the loss of water, they take place simultaneously, and this is what is actually driving the reaction forward. Let us also worry a little about the migratory aptitude, which we discussed, that this is a migratory aptitude, but what is it that our series which we gave, that the migratory aptitude of hydrogen is the maximum, followed by aryl, followed by alkyl. So, this migratory aptitude depends upon a few things which the reaction considers before favoring a particular migratory group over the other. So, the first is the nature of the group itself. Okay. So, it is the nature of the migrating group. Preferentially, the electron rich group migrates. So, the group has to migrate towards a positively charged carbon, right. So, it is an electron deficient site where it is migrating. Therefore, the group has to be electron rich to have an impact in the reaction and for it to migrate. So, for example, in this, if can be illustrated by this, that if you have this particular pinacol, under the acidic conditions, So, both the carbons are equivalent. So, anywhere you can create the carbonium ion, it would not make a difference. So, if this is your substrate and in the first step you created this carbonium ion, so the next step is now between these two, the aryl and the para-methoxy phenyl, between the phenyl and the para-methoxyphenyl, which group is going to migrate. So, when we say electron rich group migrate, so between the two it is the methoxy substituted benzene which is more electron rich. Therefore, this is the one which migrates and you get this carbocation preferentially yielding the corresponding ketone pinacolone as the major product. So, the migration of this one takes place over the phenyl because this is more electron rich as compared to phenyl. So, this is how we so whatever we are claiming is through what we have seen through the products. So, we found that this is the major product and this is what made us believe not one reaction, but many reactions which have been carried out and similar analysis has been found in all of them, which makes us make a general statement that it is the electron rich substituent which migrates in preference to the other if both have a choice of migrating. The second thing on which the migratory aptitude depends is the stability of the carbocation. So, we are talking about the intermediate carbocation and its stability. So, let us look here. You have this pinacol, okay, and the first step you treat with H2SO4 and you are generating a carbocation. So, now between these two tertiary carbons there are two possibilities of generating the carbocation. One could be, so if I number the carbons as 1 and 2, so it could either be on carbon 1 or carbon 2. If it happens on carbon 2, this is what you get, and if it happens on carbon 1, the generation of the carbocation, if it happens on carbon 1, this is what you get. Okay. So, you can get ideally two carbocations A and B. So, the question is based on the stability. The one which is more stable is the one which will be preferentially formed. So, when you look at structure A and structure B, in structure B the positive charge is on a carbon which is attached to two phenyl groups, and therefore, this is more of a charge delocalization on the two benzene rings, and this will be formed preferentially. So, if this is formed preferentially, the product from the Pinacol-pinacolone rearrangement of this is going to yield you the major product from B as the intermediate, which will then involve migration of the methyl group and formation of this pinacolone. So, this is formed as the major product because B is the more stable carbocation, and therefore, this will be formed in preference to the other, yielding you this product as the major product. Okay. The third parameter which decides the migratory aptitude is the stability of the cyclic intermediate. So, we said that during the migration a cyclic intermediate 3-membered is getting formed. So, depending upon the stability, the reaction draws its thermodynamics accordingly, that which is the one is going to form over the other. So, for this, if you look at this pinacol, in which both sides it can form a carbocation. So, there is no question of any difference between the two carbons. So, either carbons if it forms, it is going to be identical carbocation. So, we are done away with that first thing. Now, the question is between the phenyl and the methyl, which is the one that migrates. So, we are talking about one, the electron rich group migrates, right, but between the two, whichever migrates, what is going to be the effect on the nature of the intermediate, cyclic intermediate, which is going to get generated. So, if the phenyl group migrates, what is going to happen is, so this is the carbon, any of these two will migrate on this carbon. So, when it migrates, on this carbon, the phenyl migrates, this is the intermediate which you get, and if the methyl group migrates, okay, if this one migrates, this is the intermediate which you get. Now, if you compare these two intermediates 1 and 2, you see that 1 is more stable as compared to 2, because again it is a resonance stabilized structure. The positive charge is over a phenyl ring. So, it is more resonance stabilized structure. Therefore, the phenyl group migration is preferred over the alkyl group migration. So, this is from where we draw the rationale that pH gets preference over an alkyl group migration. Okay. So, based upon this logic which we have just discussed, let us take a few examples and see what are the products which are going to arise from this Pinacol-pinacolone rearrangement. So, let us take some examples to validate what we have just said. So, in this case you are having two different tertiary carbons, okay, and each of the tertiary carbons is capable of giving you a carbocation. So, the question is which is the major product. If you consider all the three factors, then you will find that the major product which should form should be this ketone. So, between this and this, which is the most stable carbocation which is going to be generated is the one which is having two phenyl rings. So, if the positive charge is being generated here, then a methyl group will migrate onto this carbon, okay, and therefore, it is going to result in this ketone. If you have, instead of this pinacol, again we have discussed already. Now, both the cases it is identical carbocation which will be formed. So, now depends upon the migratory aptitude, which depends upon the stability of the cyclic intermediate. So, in this case a phenyl migration would be preferred over a methyl migration, and therefore, the product which we expect to be the major product will be through a phenyl group migration. Okay. Try solving this one. So, I can just write in this case that here a phenyl group is the one which migrates, and in this case the carbocation is getting generated on carbon 1. Okay. So, this forms the carbocation. So, that the methyl migration takes place and you get a ketone on carbon 2. Okay. In case number 3, again it is not a symmetrical system. So, you have the probability of generating two different carbocations. So, we think that the carbon 1 which bears the phenyl group is the one which is going to form the carbocation. So, if it forms the carbocation, then there is going to be a migration of either the methyl or the hydrogen, and we have seen that the migratory aptitude of hydrogen is the maximum. So, this hydride migrates and the product which you get will be this. Okay. Let us see few more examples. So, the product should be through this hydride migration. Okay. If you are having, this is slightly different, if you start instead of the pinacol, you start with this as your starting material. So, it is not a diol, but it is capable of generating the same carbonium ion which you were getting from the pinacol when you treat this with nitrous acid. So, when you treat this with nitrous acid, what is going to happen? This is going to get removed and you get a carbonium ion being generated on this carbon. So, the question is that between carbon 1 and carbon 2, you already have fixed the position of carbonium ion generation, which is carbon 2, and now depends of these two aryl groups, which is the one which migrates. It is the paramethoxy or the metamethoxy benzene which migrates in this case. So, one would imagine that the paramethoxy is the one which is going to be more electron rich, and therefore, this is the one which migrates and gives you the product which is through a paramethoxy phenyl migration, carbon 2, and on carbon 1 you get this ketone with the metamethoxy phenyl ring. Okay. Another example, treat it with AgNO3. Okay, you are going to generate carbocation again on this carbon 2. So, the product is going to be, again there is going to be a choice between a methyl group and an ethyl group migration, and ethyl being more electron rich is the one which is going to migrate, leaving you with this acyl unit. And so, you have this carbon, I will just redraw this. So, this is a methyl and the carbon with 2 hydrogens and the ethyl group migration. Okay. Another example, if you take an example of a cyclic diol. Now, this is interesting, just look at it carefully, that if you take a cyclic diol like this, right, again this is a pinacol, both are tertiary, right. What I can do for your convenience, I just number this 1, 2, 3, 4, 5 and 6. So, between carbon 1 and carbon 6, the first thing is which is the one which is going to form a carbocation when it is treated with under acidic conditions. So, we could say that if the carbocation forms at carbon 6, it is part of a 6-membered ring, and it is going to be more stable as compared to when it is forming in a 5-membered system. So, if it generates at carbon 6, now the next thing would be there is a migration of this carbon-carbon bond. Okay. So, this carbon-carbon bond will migrate at this position, which is the carbon 6, to give you the spirocyclic ring system, in which the 2 rings are connected through this common carbon, and this carbon 1 is the one which gets converted to carbonyl. So, if I number it again, this is your carbon 6, okay. This is the carbon 1 which was bearing the hydroxyl, 2, 3, 4, and this carbon 5 now gets connected to carbon 6 by this CC bond migration onto this position. So, you get the ring expansion product, these are spiro compounds. So, what is happening is a ring expansion, a 5-membered is changing into a 6-membered ring. Okay. So, this is an example where your Pinacol-pinacolone rearrangement is giving you a ring expanded product. Okay, let us take another example. If you have a combination of a 4-membered and a 5-membered system. Okay. In this case again there is a choice whether the carbocation is generated on the 5-membered or the 4-membered, 5 in this case being more stable. So, the carbon-carbon bond migration is going to take place from the 4-membered system, so that there is a ring expansion, and in this case you will get 2 fused 5-membered rings, and this is the spiro compound which you will get. Similarly, if you have 2 5-membered diols with a difference in the methyl group substitution, okay. So, here again one of them is going to undergo a ring expansion to give you a 6-membered ketone. So, in this case again the carbocation is generated on this carbon and this migrates and forms the 6-membered with the carbonyl functionality. If you have a combination of 2 6-membered, one is a methyl substituted and you subject it to the same conditions of Pinacol-pinacolone rearrangement. So, in this case between the two, this is the one which forms the carbocation, this ring. So, you have ring 1 and ring 2. Okay. So, ring 2 forms the carbocation and ring 1 carbon-carbon migrates to give you a 7-membered ring. Okay. So, you get this 6 and 7-membered ring. This is the product which you expect. Another example, if you have this diol. So, there is one hydroxyl on this cyclic 5-membered and another on this chain. So, if I just number them for your convenience, 4, 5. So, you treat it with concentrated H2SO4, same conditions. The product which you expect, please try to do it yourself. What is going to happen? Which is the one which is going to be more stable, 6 or 1? Carbonium ion. So, at which position it is going to be more stable? At 6, right, because of the 2 phenyl groups. So, once it forms at 6, then there is going to be a migration from of the CC bond from the ring, so that it again leads to a ring expansion product with this bearing the carbonyl functionality. So, if you just see what has happened, this is your carbon bearing the OH and now a keto, and this is the carbon 6 bearing the 2 phenyls and 2, 3, 4 and 5. So, you can see that it apparently is a very simple reaction, but it results in very interesting products as a result of the ring expansion in case of cyclic diols. Another example, in case of a monocyclic diol, if you start with this, okay, and you subject it to the same condition. So, as you would expect, the first step will be the protonation followed by loss of a water molecule, so that you are going to have a carbonium ion something like this, right. Now, again there are 2 possibilities. One could be that there is this hydride migration, okay. This one migrates, right. So, if it is through a hydride migration, or there is a carbon-carbon. So, this can be route 1, this could be route 2 if there is a carbon-carbon bond migration. So, what are the 2 products which you expect? So, if the hydrogen goes here, right. So, this is going to move and you will in this case expect a cyclohexanone. right, as the product, but if there is a carbon-carbon bond migration, so what is happening in this case? In this case, instead of the ring expansion, it is giving you a ring contraction product. So you get this as your major product. So this is a ring contraction. So far the examples we studied were of ring expanded products. This is a ring contraction product, which apparently is the major product which is formed from this reaction. So that means hydride migration is not the preferred pathway, it is the carbon-carbon migration of this bond which is the preferred route. So what could be the reason for this to happen? So if you just look at the mechanism, so the first thing is we have to know about the stereochemistry of this diol. Okay, it could either be a cis or a trans. So if you are starting with a mixture of a cis or a trans, let us say in the chair conformation, how it would look like. If you start with the trans isomer, a trans 1,2 diol, it means this is what it would look like, your trans 1,2 cyclohexane diol. This is the diaxial, and this would exist in the ring flipped form also, which I will just write could be the other form, that is the di-equatorial. So both are trans isomers, the diaxial or the di-equatorial. Now in this case, if the first step, let us say, is the protonation, okay, what will happen first of all in the case of the diaxial? So for the diaxial, we saw that for any alkyl group or the hydride to migrate, the H and OH should be anti to each other. So they have to be anti-periplanar, okay, they have to be anti-periplanar for this to migrate and the migration to take place. But in this case, the H and OH, in no case they can be anti to each other. Therefore, in this particular diaxial, no reaction is possible. In the case of di-equatorial, once this gets protonated, okay, now the next step is that when it is protonated, this leaves, okay, and the leaving group and the neighboring group have to be anti-periplanar. So this carbon-carbon is what is anti-periplanar to the leaving group, and therefore what happens is that you get a carbon-carbon bond migration, which is actually acting as the neighboring group in this case and giving you only one product, which is the ring contraction product. So the CC is anti-periplanar to the leaving group, and you get only one product when you start with the trans isomer from the di-equatorial conformation. If you take the complementary cis isomer, you start with the cis isomer of this diol, in which the two hydroxyls are axial equatorial with respect to each other. So now your leaving group, okay, once it is protonated, so your leaving group, let us say, and your neighboring group have to be anti-periplanar. So if it happens from this carbon, then it is this carbon-carbon which is going to migrate. If it happens from here, then it is this hydride which is going to migrate. Okay. So in this case, you have these two options, either you have this combination or you have this combination, so that in case of this cis isomer from a hydride migration, okay, if this hydride migrates, then you get the cyclohexanone, and if the carbon-carbon bond migrates, then again you get this aldehyde. Therefore, since the aldehyde is coming from two different pathways, and if we sum up all the contributions, then it is this product which predominates when we carry out the acid catalyzed migratory behavior of this cyclic diol. Alright, so in the next class we are going to start with phenols, and we will see what are the similarities and differences phenols have with respect to the alcohols. So till then you revise your alcohols and gear up for the phenols for the next class. Thank you.